One. Good afternoon. A warm welcome to all the participants, resource person, and advisors team of ThickNess Learning Community. We, ThickNess Learning Community, are happy to have you here for the international webinar on 5G challenges and opportunities. We would like to mention that we've got 300 plus registration across India and overseas. We, ThickNess Learning Community, is a new online startup zeroing in on sharing the knowledge through collaborative studies by organizing expertise and professional talk, inspiring and motivating young minds for entrepreneurial leadership vision through various programs and accelerating women empowerment that comes to scale up the quality of their life. Our upcoming webinars are Let's Learn About Cloud, Life, Stands Our Choice, UPSC, and etc. And now I'd like to introduce our dynamic speaker, Dr. Lingasamy Veluchami, Technical Lead, HCL Technology and RF Conformance Test Engineer at Keysight Technologies, Bangalore. Dr. Lingasamy has completed his BE in Electronics and Communication Engineering at Coimbatore Institute of Engineering and Information Technology, ME in Communication System from SSN College of Engineering, Chennai, and PhD from Anna University, Chennai, Tamil Nadu. Dr. Lingasamy started his career at GTL Limited as project engineer and then was promoted as telecom engineer. He has worked in Huawei Mobility, Wixmax, LTE project. Dr. Lingasamy was promoted as senior engineer and was leading Huawei WiMax E project for Western region at Huawei, Saudi Arabia. He has worked as a JRF under a project funded by Space Application Center, SAC, ISRO at SSN College of Engineering, and then as a senior research member. Dr. Lingasamy joined HCL as technical lead, and his current experience includes as radio frequency engineer, Keysight Technologies. Dr. Lingasamy has published research articles in reputed peer-reviewed journals and conferences. Dr. Lingasamy has 10 years of professional research and industrial experience encompassing designing, analysis, and testing of antennas, RF conformant testing of LTE, C-V2X, and 5G modems, and telecommunication network implementation. With this note, once again, I'd like to welcome our resource person and all the members of ThickNess Learning Community to this international webinar. Over to the resource person.
Thank you, Mr. Kritik Raja, for the nice introduction. So let me share my screen. Thanks to ThickNess Learning Community as well. So good afternoon, good morning, and good evening to one and all present here, because many engineers are joined from different regions and different time zones. So I must thank Kritik Raja and Shanti Madam and other of ThickNess Learning Community members for providing me this opportunity to share my knowledge on, share my thoughts on the 5G, especially on challenges and opportunities. So this is my topic, and so this is my agenda for the day. I'll be briefly discussing about a brief introduction to the 5G, and followed by the evolution and features that are special about especially there in the 5G, and various deployment scenarios. So that was the unique property we see in especially in 5G, and different use cases in the different perspectives, and that we'll be discussing about. And so one particular theorem that come into mind when we have high capacity, when we talk of high capacity, large data rate, everything, one particular theorem comes into mind is Shannon's capacity theorem. So how it is interrelated over here, so that we'll see, and what are all challenges and opportunities, especially in the RF and antenna domain and testing, so different aspects. So we'll be discussing on that, followed by what kind of simulation scenarios and testing procedure or test ranges are for being used in the 5G, that we will be discussing, and some followed by to conclude we'll be discussing about some of the design tools and testing testing equipments, and followed by I will summarize my talk. Okay, so now we will start with the introduction to 5G. So in 5G is a technology where from the beginning, so you can see that in 1G we had analog telephones, And in 2G we had GSM based technology where we could able to call and as well as the text message. So, and in 3G what has happened is that in 2G 2.5G there was 2.5G was there where they could improve a small amount of data. But in 3G, it has improved to, for example, 50 Mbps or 81 Mbps when we go for multi-carrier technology. And in 4G, the speed was improved up to 150 or 180 Mbps. So if you see that till this point, you can see that the data speed was incrementing and call quality was improving. So that is what is the evolution happened. But especially in the 5G, there was a rapid development, and it has revolutionized everything in the network. Okay, so that is the specialty of the 5G that we will be discussing shortly. And you can see that the unique, the first property comes into our mind is that spectrum. So far we have been using sub 6 gigahertz. So that's why we had a cell coverage type, cell type of coverages. Now we are going for millimeter wave as well, mainly because of bandwidth. Because some of the licensed bands are available. Even in some area we can see that non-licensed bands are also available. So that is why that leverage we are taking up in this. So what all frequencies can be used, that has been done by several experiments were done by several universities. So that I will be discussing shortly. Okay. And if you consider the antenna technology from 2G to 4G, you can see that single input, single output for 2G, and in UE side also we have been seeing that single input, single output until 3G came into picture. And the what smartness they introduced in the 3G is that they provide a remote electrical tilt unit and RRH concept. Because earlier you will have very big base stations in the for 2G especially, and later they provide a concept called a remote radio head radio, which means in tower you could have seen small radios are available. So that way they save the space, and then they provided some kind of flexibility in the deployment. In 4G, you can see that the MIMO came into picture. So that is mainly for improving the bandwidth, okay, data rates, and then the quality of voice and everything, and so on. Okay, in 5G, we can see that massive MIMO come into picture. Massive MIMO means so each MIMO array. Each MIMO will have a phased array, so you'll have several millions of elements will be there. That is grouped as massive MIMO kind of thing. So that will be discussing. And beamforming concepts. So mainly used in FR2. Here FR1, FR1 is nothing but sub 6 gigahertz. FR2 is nothing but in millimeter waves. Okay. So in beamforming, why we go for beamforming, that will be discussing shortly. And antenna arrays and N-cross N MIMO we will be using in the UE point of view. So if you look at this diagram, you can see that until 4G we have been using cell type of coverage. You will be seeing 3 antennas in the tower. So each cell will be covered approximately to 120 degree each cell, so that you can cover the entire 360 degree. But that will not work for 5G technology, because we are having a high SNR requirement and a low battery requirement. So several stringent requirements are there in the 5G. So that's why they have gone for beamforming approach. Okay, beamforming for each device will be especially connected with the beamforming technology. Okay, and now let's move on and see the deployment modes, different deployment modes. So far I have been discussed. So first deployment mode is non-standalone mode, which means, see, now we have been using network operators have invested a huge amount in this, billions of dollars in for LTE network. So now suddenly they cannot just remove this one and then deploy NR or 5G technology. So that's why they go for, that OEM vendors are giving an opportunity that you can use existing LTE as well. You can add 5G, some of the features of 5G along with the LTE network. So that is called as non-standalone method. So here you can see that, one second. You can see that, control and everything will be done at the LTE network itself, the green line. Okay. In NR, what it will happen is only we will have data plane will be there, which means we will get improved data rates. That's all. So that is called a standalone, non-standalone method. The next method is in future. In future, what will happen is we will discard this network. We will isolate this network. You will have a separate 5G network. You can see that LTE network will be separate and the 5G network will be separate. So in this case, it is called a standalone, which means 5G will stand alone in their network process. Here, the control and data will be handled by 5G core itself. Whereas here, you can see that control will be handled by LTE network, LTE core network, but only the data plane will be handled by NR. Okay. And the third approach is that dynamic spectrum sharing. So here, you can see that 5G will be implemented in two technology. One is two frequency spectrum. One is sub-6 gigahertz, other one is millimeter waves. Okay, in sub-6 gigahertz we have a 4G also existing. Okay, so that's why they thought that okay, we can share whenever application require. For example, I require below sub-6 gigahertz. Whenever 5G requires some band, then that will be used. Okay, if 5G is not active, then LT will be LT. Only LT devices are available. Then LT will be reusing that spectrum. Okay, so that is why it is called as dynamic spectrum. It is very much powerful and very much cost, especially spectrum efficiency will be very much high in this scenario. You can see that your 5G base station available and 4G base station available. So when 5G mobile comes into picture, it will be communicating through this band is millimeter wave, and this one is sub-6 gigahertz. So it will be 5G device will be able to get in touch with the sub-6 gigahertz 5G as well as the millimeter wave 5G. Okay, so when LTE device is comes into picture, so it will be the same spectrum will be reused for 4G technology. That is why it is called as dynamic spectrum sharing. Okay, next we can see that RAN architecture. So here RAN architecture, there are number of RAN architectures even proposed in LTE itself. LTE itself, we have a LTE and a basic LTE and a LTE advanced is there. So some of the RAN architecture already been adopted. For example, one such architecture is that distributed baseband, which means here, see, both L1 and L2, so all control related things from between core and this one will be moved to radio itself. That is called the control will be distributed to the radio itself. So that radio means you can see that base station. Okay, base station or E node B, we call it as E node B, or in 5G we call it as G node B. Okay. So when you move that, what is the great advantage is that you can improve the speed and you can reduce the latency, because if you have a base station and BSC and backend core, everything is there, means so there will be a high good amount of delay is involved and good amount of resources involved. So that's why they thought that okay, we will move all those control into base radio E node B or G node B itself, so that we can avoid those in scenario. So this is mainly used in the, for example, when you want to deploy a network on very quickly, then we can use this kind of RAN architecture. I believe some of the operators are already implemented. I believe that Jio also, Reliance Jio in India, they have done this as well. That's what I believe, because they could manage to implement the network within 6 months. So they could have followed this kind of scenario. The next good scenario is that virtualized baseband. So here you can see that virtualized baseband means, so L1 and L2, layer 1, layer 2, physical layer, MAC layer, and data link layer. So all these layers are processed in the virtually. Okay. So when we do in this manner, what will happen is we need not, for example, if I am adding one particular feature in the 4G, for example, in LTE they improved. Initially they were giving a normal voice call. Later they added a voice over LTE. Okay, if you want to do that, you have to do significant change in the whole network. So in that case, what happens is it will take time, consume time, and also a cost also involved. And you will have to wait for some months to implement it. So, but in the virtualized baseband, what is the great advantage is that you can, if you want to add some new features, you can add it. So the baseband is virtually processed. So hence you can able to process, you can able to generate and add any new features whatever you want. Okay, that is the great advantage in this virtualized baseband. The third one is centralized baseband. So centralized baseband is nothing but you will have a lot of few number of distributed basebands. So in that case, for example, small basebands are available. For example, you can see that a small office coverage, indoor coverage, and stadium coverage. So these kind of networks and all, it will be very small, but for that you cannot implement a whole RAN network. So what we can do is you can do baseband processing. You can do at a centralized manner. You can keep your all this baseband processing unit at what particular location. So you can control all those. For example, in a whole city, you might be having several indoor in-building solutions, and some kind of status will be available. For that, they will be providing some kind of coverage. So that entire processing will be done at centralized manner. Then you need not have to invest much on that network. So that is why they go for this kind of architecture. So still some more are there. So that will be discussing in shortly and on the go. Okay. So now we'll move on to 5G use cases. So use cases nothing but when you want to you have a network, so you want to use it for particular applications. So how well you can plan within existing network, how well you can plan for a particular application is nothing but use cases. So here first use case is that enhanced mobile broadband. Okay, so with the proposed architecture of 5G, we can achieve enhanced mobile broadband, which means in terms of GBBS, you can able to achieve the data rate. The next one is MMTC, massive machine type communication. Here, in future, you are going to see that billions of devices is going to be connected to the network. Okay, that's why. So in order to handle that, we need to have 5G has that option for that. In future, they predicted that billions of devices is going to be connected, and your home, your cars, and everything will be connected through this with this 5G network. So that's why that is one of use case called as massive machine type of communication. The third use case is ultra reliable low latency communication. So which is mainly used for wherever you have criticality, for example, remote surgery and so on. Okay, so that is where these use cases will come into picture. Now we'll move on to the applications, some of the applications. So in enhanced mobile broadband, of course, you can able to download a full HD movie in seconds or a minute. Okay, so that is have ultra high speed data rates. The second one is that 3D and ultra HD video streaming. You can just see as a live. You can see the videos in live, and real-time games. So nowadays you can see that the games are becoming more and more heavier, so that you must require good amount of data rate, so that you can feel the game. You can able to play the game with a full of good you will get a good feel whenever you play the game. Otherwise, if you have a slow connection, you cannot play the real-time game with satisfactorily. And next is that augmented reality and virtual reality, which needs speed as well as the latency as well. So that's why I placed near to this, in between these two. Okay. Next is that ultra reliable low latency communication, which means autonomous cars. You can see that in future all cars will be connected together, and it will be autonomous driving also option also they are yet to provide. They have done several trials. Now they are going to implement. Recently I heard from I noticed in one of the article is that by 2021 in US they are going to make all the car manufacturer to compulsorily install that CV2X mode, cellular vehicle to everything modem, which will be mainly used for autonomous cars. So you can able to monitor whenever you are driving in a speed in such a very good speed, for example 200 kilometer speed or 180 kilometer speed. With that time itself, it will just guide you to, for example, if you are feeling sleepy, that will wake you up, and then a car automatically will drive through, and it will handle all the situations. So that is where autonomous car comes into picture. And if you want to drive, if you don't like to drive, then a car itself will drive for you, because it will be able to communicate with the many pedestrians and traffic lights, and it can able to detect the humans and everything. So here the processing will be huge, and then it will be very low latency is required. In terms, it should be in terms of microseconds or milliseconds. Otherwise, what happens is, if you are not processing in that speed, what happens is the car may hit in somewhere. So that is the criticality they have. And the second such application is the remote surgery. For example, now the doctors are guiding from the remotely, and then one engineer or some a tech specialist will do the surgery at one point. But in future, doctor will be sitting at somewhere, and your patient will be sitting at some hospital. He will do surgery from the remote itself by using mouse. Okay, and wireless control of industrial process or production process. For example, you are you are producing some laptops, you are manufacturing, or you are assembling some laptops or industry. Now also it is available, but in future it will be even more faster, and then reaction will be very quick. And the fourth one is smart grid distribution automation, which means this will be need-based smart grid. For example, so if I am using in peak time, in the home, if load is very heavy, and then several people are using, means they can, it will generate automatic messages to some of the house that don't use heavy machines now. Heavy, for example, grinder or mixer or something else. So you can use this particular slot so that this load will be normal. Like that, you can automatically generate the messages, and then so that you can balance the load. So we can avoid the even power shutdown also in between. So that is the one criticality we have. Then if you talk about MMTC, massive machine type communication, you can see that industrial IoT. That is where we are talking about. Like in industrial IoT is nothing but your, for example, one particular example is that you have several boilers will be there in the industry. Okay, in some particular industry. So you have to monitor the temperature and each boiler, and you have to send it to the some of the a person cannot go there and monitor this and then come back. So that's why they use industrial IoT to monitor. And you can see that in oil companies, they use for for example, if some breakage is there in the pipeline or a leakage is there in the some pipeline, they can able to detect using this kind of industrial IoTs. Okay, and smart agriculture. So now this has been implemented so far, but in future it will be connected to the cloud, and then you can process it easily, and it will collect the data of and the harvesting, all the details, and then you can it will give you provide guidance on the smart agriculture. The smart cities, smart grid, this we have been talking several years as well. And smart home and building, which means your complete home will be automated, and then when you get in, it will get lights getting on in a fraction of a second, because that processing will happen. This was discussed, IP multimedia subsystem, like that, several years back they have done, but later I don't know what has happened. It was not implemented that importantly, but now they are coming to picture. Smart transportation systems, and then health monitoring wearables, which means your patient will be attached with the several small device wearables will be attached in the patient body, so that the monitoring can be done by a doctor sitting at somewhere, even from some other country. So he can monitor the health condition of the patient by remotely. That kind of scenario we can able to achieve, because so machine time means many devices will be there, so you have to coordinate with each other, and then you have to predict the actual scenario. These are the overview whatever we have discussed now. And you can see that extreme mobile broadband, what all the applications are used, and massive message type communication, what all the applications are being used, and then ultra low latency communication, what are all there. And you can see that here you can talk of machine to human talking. And especially the wearables are but nowadays in defense they have been using a large scale, because they want to monitor the health of the soldier who is working in the border, because in so far they don't have any data how is he and what kind of food he is eating, and what kind of scenario they cannot predict. Now they are slowly implementing wearables, so that they can monitor their health condition, and where they are going, they can able to track everything. So that kind of things are going on. And so now the what is so special about 5G? One is very high data rates. How it comes? Why, that also we need to consider. One is large spectrum. Okay, large spectrum in which we have licensed, unlicensed, and also millimeter waves. Okay, and deployment of smaller cells. So large spectrum, I mean large bandwidth we can able to use. For example, in 3G, they have been using, I think, 20 megahertz, 15 megahertz, I think, 5 megahertz, sorry, 5 megahertz. And later they improved. And into 4G with or LTE, they have been using 20 megahertz. But in 5G, so far they have been implemented 200 megahertz. Now they are moving into 400 megahertz. In future, it may be 1 gigahertz also bandwidth. So that kind of bandwidth we can able to use. Second thing is that deployment of smaller cells, because why we go for smaller cells. When frequency increases, the coverage range will be decreases, because lambda is wavelength is inversely proportional to the frequency. So here we are going to use millimeter wave, so we cannot cover a large area. Hence we go for smaller cells. And when city will be covered by several huge amount of smaller cells, that's why called as ultra densification. And use of multiple input and multiple output systems in order to enhance the data rates and enhance the speed as well as. Okay. And beamforming technology especially is being used for especially the beamforming technology they are going to use for even sub 6 gigahertz also. Why we go for that is that the stringent conditions provided by the 5G is that, so you should not pump this much power. For example, I think 40 dBm, I think. We can able to transmit the power. So beyond that, you cannot transmit. So if you want to achieve the coverage, for example, if a person is standing at some particular distance, X distance, you want to give a good amount of coverage, then you have to have a beamforming technology only. Why we go for beamforming technology? Because beamforming means instead of having a full cell coverage, I will go for multiple spot beams. So that I am saving the power. For example, if I transmit in the whole sector, what happens is I am wasting this power, because users are only 3 users are there, but I am wasting the entire region. I am covering entire region by wasting power. So in order to avoid that, we are going for a beamforming technology. The second advantage is that you can improve the gain also. See, you are using 44 dBm power, for example. Okay, 44 dBm power, if you transmit to the whole sector, it will be very minimal for the receiver. So if you send in 3 sectors, 3 small beams, what happens is you can able to the power will be very much higher when compared to the cell coverage. The third advantage is that the 3GPP has given very stringent, and FCC and IMT 2000, they have given very stringent condition is that your battery life of the UE or your mobile should be very long. Okay, so in order to achieve that, you cannot your mobile keep on sending updates for coverage, or say getting registered with the node B. Okay, so in order to avoid that, they go for beamforming technology. Okay, and high spectral efficiency can be achieved by using multiple access techniques. I think OT, FDM, orthogonal frequency division multiple access is being used, and advanced modulation and coding schemes, which means so far I think in LTE they have been using 256 QAM up to 256 QAM, because I have validated the device up to 256 QAM. But now they are going for 1024 QAM as well. So advanced modification techniques are there coming to picture, because you can see that in this curve you can see that capacity increases whenever you increase the number of bits being processed. So order of the modulation, for example, 1024 QAM is giving, for example, 10 bits per second, hertz per second capacity, whereas in QPSK you can see that 2 bits per hertz per second. So this is how we improve the one is spectrum, the other one is by improving the modulation scheme. By increasing the order of the modulation scheme, we can able to improve the high data rates. Okay. Next one feature is that massive MIMO along with beamforming. So massive MIMO means you will have, so in order to provide several multiple kind of beams, you cannot use single antenna. You have to go for array kind of antenna. So each MIMO element will be an array. Okay, so you will have plenty of thousands of elements will be constructed in a plane, so that you can able to do beamforming whichever direction you want. For example, you have to cover 360 degree. You can only accordingly you have to design this beamforming algorithms, everything. And next is heterogeneous devices and application. Heterogeneous, I mean, you will have so far, for example, in your network, mobile is connected. So in future, everything will be connected. For example, devices, vehicle, and your medical devices, IoT devices, and LoRa and Wi-Fi, and you can see that. So LoRa, Wi-Fi. So these are all will be integrated, will be an integral part of your 5G. For example, 3G, 4G, Sigfox, Wi-Fi, LTM, and LoRa. Everything will be, so each kind of devices will be connected with each technology. So all are coming together, and will be will be integral part of 5G. So that's why we call it as heterogeneous devices. So a lot of IoT devices will come into picture. So different kind of devices with a different architecture and everything. So that's why 5G give a platform to accommodate those devices. Next is a machine type device to device communication. Now we can see that in small scale we have been doing. You might have experienced Bluetooth. Through Bluetooth you are sharing the files. Okay, that is a device to device communication. And now also you can see that in car you can see that a small radar is inbuilt, so where you can track any device, any vehicle is coming near to you or not. And in some of the Volvo trucks and big Mercedes Benz trucks and all, if it find any car, any vehicle comes into suddenly, then it will put brake automatically. So that kind of device to device communication has happened. And ultra reliable communication vehicular networks is that. And low data, when we talk of low latency, so how we achieve low latency, that is also a big deal, because one way of achieving is that you can use higher frame structures, and then you can do that. And also you can reduce the TTI. We used to call it as TTI, total transmission. I think total transmit time, which means signal from the origin to the device, and device how much time it will take. So in LTE it is 1 millisecond. Okay, and in 5G it will be less than 1 millisecond. So you have to reduce the TTI. So which means processing speed should be very much higher in this. It should be much higher in this 5G network. So that is one way. The other way is that you are integrating the protocol stack with the core network, which means, see, you are giving you are offloading the most of the processing at the node B level itself. So that is another way of doing in the improving the low latency. Which means what I mean to say is that, so instead of, for example, if an application request for, if a mobile request for some service, so what base station will do? It will ask core to authorize this. It will ask core whether he is a registered, properly registered user or not, and it will get authorized from there. Now they are moving some of the intelligence to the node B itself, so that it will process very quickly, and then only for small things it will go to the core. Okay, that's how they are integrating the design protocol stick at lower level itself, and moving intelligence to the edge of the network. That's what I have been discussing. So most of the intelligence are being moved to the edge of the network, so that the processing will be done at the edge of network, so that your mobile gets low latency communication, high data rate, everything can be achieved by this. The third approach is that network slicing. So which means, for example, I'm adding new feature or new use case to the network, 5G network. What happens is I have to modify the entire network in order to accommodate the. So far, it have been like this. If I want to add some feature, I have to modify entire network. But in 5G, it will not be like that. So why? Because they are going to employ a network slicing method, which means for example, EMBB slice, it will follow the different route of different architecture. And if I go to URLLC, there it will have a different kind of architecture, and IoT slice will have different kind of architecture. If you want to add some of the feature in the IoT, only this network can need to be modified. This part only need to be modified. So you need not modify entire network. For example, if I am adding some of the feature to the URLLC slice, then you need to modify only this, not entire thing. So that is a great advantage we have with the 5G. Now, as I have been telling, so we have done with the key enablers for the 5G. And now we will see basic fundamental thing, theory behind the high data rates. So which is quoted by Shannon's capacity theorem. So it was very much powerful theorem, because the capacity is directly proportional to the operating bandwidth. So I have been discussing that when we have a large bandwidth, they can able to achieve high data rates. That is one thing. The second option is that you can use number of receiving antenna, so that you can process the data quickly, and then you can improve the data rates capacity. Third one is that SNR. If you have poor SNR, what happens is error rate will become very high. So in that case, what will have a number of retransmission will be happening. So in order to avoid that, we need to improve the SNR. Next is that number of TX antennas. So transmitting antennas also will be much high. So how it is interlinked to the 5G is that, so see, in transmitting antennas, here we are going to implement massive MIMO. So which means huge number of thousands of antennas will be there at the transmitting side. So we can improve the capacity by this. And SNR, how it is being improved? Here we are going to use beamforming technology, because each user will be will be provided, will be serviced with the individual beams. So that you will have an improved SNR. The last one is that channel matrix. So here only the signal processing engineer will come into picture, so that you have to process the channel, and then you have to decode the correct data. So how here you can see that several engineers will have opportunities. For example, antenna engineer, and spectrum plan. Like if you are much interested in the communication, you can go for how you are going to optimally plan this bandwidth that is there. And the antenna engineer will plan number of how you are going to design number of antennas. So that kind of project we can do. And if you are good in mathematics, you can take up this project. For example, channel matrix, how different kind of channel matrix we can propose, and then in order to improve the capacity. So this is how opportunities will come into picture. Next is that frequency of operation. I have been telling they will not select frequency randomly. Okay. So what they will do is they will do huge number of measurements. Okay. You might have heard Rappaport. Your Rappaport book for communication is very famous. Okay. So before we move on, so I will let you know a few things in subsist gigahertz. So we have been using 900 megahertz for the 2G. Okay. So they did not come with randomly come with the 900 megahertz. Okay. So they have done a lot of measurements. So how they consider is they will do a lot of measurements. They will consider different kind of blockages. For example, concrete wall, wooden breaking sliding, and aluminum sliding, and metal walls, office furnishing, everything they will do. Okay, what they will do is that, see, you will have you will have antenna here, and you will have this particular, for example, concrete wall or anything. You will have receiving antenna. So they will transmit the signal in the one frequency, and they will measure how much attenuation happened because of this wall. Okay, and similarly they will try other frequency. So likewise they will try multiple frequencies. Finally they will come into picture from this chart. If you plot, for example, frequency versus attenuation, okay, they will come to know which frequency gives. For example, if attenuation is much higher in some frequency may be much lower. So this particular frequency they adopt for a particular technology. So that is how they predicted. You can see that for 900 megahertz, you can see that 7 dB for concrete wall, and so these are all the different attenuation what they got for different things. Okay, and 2.4 gigahertz, you can see that very minimal attenuations are there. So that is how they design. Even in millimeter wave also, they have done that measurements and then found that. So some of the frequency, you can see that sea level attenuation. You can see that. So these particular windows are there, right? For example, these particular windows, we are getting very minimal, relatively low attenuation in these particular windows. Okay, that is why they have chosen. For example, you can see here, it is relatively low. Attenuation is there. That's why they have chosen 28 gigahertz and 38 gigahertz for 5G. Okay, 26 to 28 and 38 gigahertz they chosen for 5G. And also in 70 gigahertz also they have one more window where we are getting a relatively low attenuation. They also have a proposal for 70 gigahertz, about 70 gigahertz. They have a proposal to implement the 5G as well. Okay. And so this is how they select the frequency of operation for anything. Okay. Next is that to summarize, so low frequency we always go for mobility and reliability and coverage. Coverage. Why we call coverage? Because your lambda is inversely proportional to the frequency. So whenever frequency increases, the coverage lambda will be decreasing. So which means range will be decreasing. So coverage range will be decreasing. Hence, so low frequency we always use for coverage and mobility and reliability, everything. So high frequency we always use for massive throughput. Because high frequency, for example, why they say high frequency means high capacity. Why we say? Because for example, 2 to 4 gigahertz. If you are having bandwidth means, for example, okay. So how much is the bandwidth? It will be 2 4 plus 4 for 6. 6 by 3 will be 2. So 200% 2:1 ratio you will get a bandwidth. Okay, but which means for example 200. If for example, okay, sorry. Okay, for example, if you are about 2 gigahertz, if you want 10% bandwidth means what will happen is, so it will be around 10% means what, 200 megahertz bandwidth. Okay, so in 40 gigahertz, what will be the 10% bandwidth? It will be 4 gigahertz. So that is why whenever we go for high frequency, we'll have a higher bandwidth. Okay, that is why they go for higher bandwidth. Next is that you can this one particular 5G antenna, implemented antenna they use. So and also one more scenario they consider is while predict while finalize the frequencies, that what are all the coexisting frequencies, because LTEs will be there, 2G will be there. It will not be wiped out in a single day. It will be taking some much time. So it should not disturb the existing communication. That also we have to keep in our mind. Okay, and so these are all the some of the mobile antennas. You can see that in this frequency range how it is evolved. You can see that. So mobile antennas being evolved. Now these are the frequency bands that are frequency bands that are proposed by 3GPP. Okay, so 3GPP, to say a few words about 3GPP, is that it is the third generation partnership project. Okay, they have a generic standards. For example, if new technology come into picture, for example, LTE came into picture and 5G, so they will provide some kind of stringent conditions that it should have this kind of properties. Okay, so that is what they give, and they proposed a frequency bands. For example, FR1 it will be 410 megahertz to 7125 megahertz. FR2 will be 24 megahertz to 52 gigahertz. Okay, and these are the frequency. In that itself, sub bands will be there. For example, N257. These are the band number. Okay, and N257 is 26.5 to 29.5. I believe the N257 is allocated for Asia Pacific, and N258 is allocated for Japan, I think. Okay, N260 and 261 is for some other countries. Okay, and N257, next to one parameter is that subcarrier spacing. So it is also mainly used for subcarrier spacing, which means if you want to discuss, it will take much time. Okay, subcarrier spacing also play a major role in data rates and latency. So whenever we have a higher subcarrier spacing, we'll have, what will happen is low latency communication can be achieved, and also higher bandwidth can be achieved. Okay, and one more thing is that, so we can use simultaneously FR1 and FR2 with the coexistent. We need to have this kind of order. For example, you cannot use randomly. So N8 band in FR1 can be clubbed with the N258 of the millimeter wave. N71 band of the sub-6 gigahertz can be clubbed with the N257. We can use this can be coexisted in the NR network. Okay. Now we'll talk about key challenges and opportunities. Okay. So far we have been seeing that some of the so to summarize for a few words. So we have been seeing the different architecture and everything, and different features of the 5G, and what are all the enabling technology that has been especially implemented in the 5G, and also what all the frequency bands are used, and what all the use cases are there. So in that, you can take up, if you are, for example, if you are a data scientist, you can take up the project on processing the huge amount of data for example, massive machine type communication. You can process the data. In order to process the data, what kind of data processing algorithm can be used. So that I explore. So now we will be discussing key challenges in the lower layers, which means RF front ends. So we'll be discussing about key challenges and opportunities. So in order to go for premise, so you can see that how antennas are evolved for different technology. Antenna, I mean, it along with the RF board itself, the whole whole system itself. See, initially they had antenna, external antenna to cover, get a very good coverage. It's a loop antenna. Okay, they had in the 1G. Okay, in 2G, what happens is initially they used external antenna. They later they embedded the antenna within the mobile phone itself. And 3G, they have used multiple antennas for multiple services. For example, Bluetooth, Wi-Fi, and everything. So they came into picture, and small antennas have came into picture, because in 3G they have used some kind of different bands. So next, because the 3G has to coexist with the 2G, that's why we have to go for multiple band antennas, and that cannot be placed in one place. So they have been going for multiple places. And 3G and 3G, you can see that antennas are and 4G. One second. So in 4G, the MIMO came into picture. So they have to alter the entire design. So, and 5G, it will be a massive MIMO kind of thing. Massive MIMO design came into picture. Okay, and this is how antenna is evolved. Antenna is evolved. You can see that. See how much big is the mobile. Now you can see that the small compact mobile. You are having number of features. For example, in 2G we had only call and SMS facility. But in 3G we had some good amount of data rates. But in 4G we'll have a further improved data rates and voice over LTE kind of calls. Okay, so it's much more quality than the other 2G, 3G or 2G, 3G calls. Okay, so that kind of features are involved. Okay, so this is the mobile perspective. Okay, when you consider the base station perspective, how the antennas are evolved, you can see that this is the 2G antenna you will see in the tower. Okay, and these are all the antennas being used for in-building solution. When you visit super shopping mall or somewhere, you can see that the small antennas can be there in the in the top of you, and on the false ceiling and all. They would have installed these kind of antennas. Okay, and this is for mainly for in-building coverages and small range coverages. Okay, in for 3G to 4G, what happens is they used multiple band antennas, because in 2G to 2.5G they had only two bands, 900 megahertz and 1800 megahertz for one particular region. Okay, in when they migrated to 3G to 4G, what happens is that they have to use single antenna for 2G, 3G, 4G, everything. So that's why you can see that how many number of ports are there in the particular antenna. One particular antenna has this many number of ports. Okay, so the coexistence came into picture. So the how complex is this design? So here two or three engineers has to work, which means antenna engineer has to work along with this, and the RF system engineer, because they cannot just coexist all these antenna. RF system engineer should play a major role here, and signal processing engineer also should play a major role here. Okay, and you can see that in 5G even more complex, because you can see that we are massive MIMO come into picture. You can see that how many antennas are the antenna elements are there, how many connectors are there, because they are going to here, I think 8x8 MIMO. Okay, and this is the 5G radio. Okay, so this is the antenna and this is the radio. They connected 4x4 MIMO radio with the antenna. So how many connectors are there? So these are all the kind of phased array for beamforming coverages. Okay, in India they are building the 5G testbed. Apart from as a part of that, Samir has developed one kind of I think 32 transmitter, 32 receiver, massive MIMO antenna. The design, a compact antenna, how it is. So how complex is this design? Because in this antenna it is not a simple antenna. It will have a phased array and a phased array beamforming algorithms need to be deployed, because when you are a signal processing engineer, you need to design different kind of beamforming algorithms, and you will have a lot of RF components, switches, and different passive or active components will be there. So everything will be there inbuilt. Okay, now it is just not just antenna design engineer. You will just design a dipole or a patch antenna, nothing like that. Okay, you need to have a multiple kind of knowledges, so that in order to design these kind of antennas, whenever the complexity increases or coexistence increases, you need to be very smart, and then you need to know you have to integrate multiple technologies together, because you need to know all the RF technologies, and you need to integrate the many devices together to form an antenna. Okay, so So beyond that, you can see that in 5G, especially 5G, you can see that, see, these many number of components are there. You know, one small mobile, we have this many number of components are there. Sorry. Sorry, this is the LTE phone. So you can see that MIMO antenna, see how much space they have given for MIMO antenna, very, very small space that has to coexist with all other RF components, okay, and all RF and baseband components, okay. You can see that this is how many number of devices are there, Bluetooth antenna, Wi-Fi antenna, and LTE MIMO antenna. So number of PC CDMA, SCDMA antenna, CDMA, which means for 3G. So number of antennas are increasing, keeps on increasing, number of devices are keeps on increasing, but mobile size not going beyond that, because now even more it is going in slim manner. So now how they are implementing is that they are going for MMIC or system on chip concept, okay. So now platform is, several platforms are open for system on chip concepts, okay. And you can see that antenna design evolution, how it has happened. So initially they have been designing simple loop antennas, okay, in the year 1983. In 1999, what happened is this external antenna become an integral part of the mobile itself. So 1999, they have a 2G mobile antenna was like this. And 2004, 3G antenna, you need to use multiple antennas. And in 2008, they had multiple frequency antennas at even a small segment of the mobile can be mobile can be used for design, was used to deploy the multi-band antennas. Now you can see in 5, when you are moving forward to 5G, you can see small piece of antenna will have multiple frequency support and everything. So you can refer this Fractus Antennas website for this. So you will get plenty of details if you are keenly interested in antenna design and RF system design, and if you are good in signal processing engineer and everything. So you can please go through this website so that you will get a good you can explore for further on this. So because if you are planning to do project on this, okay. And you can see that so in 5G, especially in 5G baseband processing, digital, these are the basic architecture. And here the main thing is that here this part is very critical in 5G, because you are going to implement massive MIMO array, okay. So you have to generate multiple beams at simultaneously, and that also moving here and there, okay. And now we'll move on to the RF and antenna system, how it is very critical, and what all key challenges are there, what all opportunities for us to explore. That's what we are going to think. So far until 3G, the antenna design was separate, okay. Antenna 3G or 4G also, antenna design will be done by separate engineer, and then they will integrate with the amplifiers and other devices, other baseband systems in the mobile or base station or whatever it may be, okay. So now it is no more, I believe it is no more possible now, because we have to go for, while designing antenna itself, we have to integrate with the amplifier and then design, that's all. So otherwise, what happens is you cannot match everything being together. So if you design separate antenna, massive MIMO antenna, and you finally you have done fantastic job, and then you have designed everything. Finally, when you integrate with the amplifier and RF mixer, baseband system, what happens is that you will get a lot of problem with the matching. So that's why we are going for active integration itself. Okay. Next is that now feature RF front end modules are becoming very miniaturized. Getting smaller, but you will have plenty of requirements. But RF front end modules are becoming very smaller, much smaller. But you have plenty of requirements. So that way, if you are a signal processing engineer or so you have to be multi-skilled, because you have to be good in signal processing, mathematics, and then RF front end design, RF designer, and also you should be an antenna designer. So you have to have multiple skill in order to accommodate these kind of things. And next we are talking of system on chip. Okay, system on chip in this, that one particular chip, flat chip system, and system on package and everything. So you cannot design separate antenna and then integrate with this particular board or PCB. Now, in PCB, what they will do is that in 2G or 3G mobile, what they will do is that they will allot a space for particular antenna, they will allot a particular space. Okay, they will allot, for example, if it is a mobile. Sorry. if this is the mobile, they initially they allocate this space for example, this space for antenna. You can design and then accordingly, and then you can integrate with the PCB. Now it is no more possible because every amplifiers, everything will be system on chip. So that you have to design on the go. You are even if we are going for multi-layers. So one layer will be for amplifier, one layer will be one layer mixer will be there, one layer low noise amplifier will be there, one layer receiver circuit will be there, one layer transmitter circuit will be there. So with all these things, so that's what we can see. I have been seeing that some of the people will do work on multi-layer board, and where you will find all the things, transmitter circuit module and massive micro antennas, everything will be there. How they are connected through wires and the various track and next is beam forming and beam switching. So this part I will take about 1 minute to discuss. See why we go for beam has to track that person. Okay, that is called as tracking, beam tracking, and also beam switching as well. So beam has to switch between you will have a huge number of arrays will be there, and so by exciting each element you can able to switch the beam. That will be discussing later. Okay, so your beam has to follow that user, particular user. When he moves here, this beam has to follow. Otherwise, what happens is this user will lose the communication and packet loss may happen. So that's why. So beam forming and beam switching is very, very critical, because in radar you might have studied that some of you might have studied in radar communication, where they will use a direction of arrival and a direction of direction of arrival concept. Okay, how the which direction you for example the enemy radar is moving, so that way they will find out where is that exactly that enemy radar. So direction, based on the direction of arrival signal, they will find out where is the enemy radar technology. Okay, so similar that direction of arrival concept also being used here, because your beam has to follow this direction of it has to detect the user, and then it has to follow the speed as well. So a user is not moving just by 10 kilometer speed or 5 kilometer speed. A user may be moving in hundreds of kilometer speed. I think in some of the article I read that even it supports for more than 180 kilometer speed. I think 200 300 kilometer speed. Okay, so that much speed it should be there. So in that case, what kind of opportunities are there? One is switching capability of these switches. Okay, that is major role, that is plays a major role here, because that latency is switching speed should be very much high. So you can design the different kind of switches and then propose for this particular solution. Second is the direction of arrival algorithm. You can you can adopt SVD method. Many methods are there. So you can propose the method. For example, if you are very good in signal processing, you can propose different algorithms for this. You can take up the project on this direction of arrival algorithm, and then you can propose a new algorithm as well. Or you can compare the different algorithms and then propose new algorithm as well. So that is opportunity, main opportunity for signal processing. Mathematics. If you are very good in mathematics. Next is that if you are good in antenna designer, you can design an antenna array by integrating switches and everything, active antenna array. And you can work with if your friend is very good in RF design, for example switches and active circuits, oscillators design. Okay, you can get in touch with your friend, and then you can both together you can design a multiple switching antenna array. You can even you can simulate you can simulate a scenario also. Okay, so that can be done. And if you are good in network engineer, so this acquisition tracking can be done in, you can consider this as a node. For example, you can consider this user as a node. Okay, so you can create a scenario where user is moving this particular speed. So you have to create a network algorithm in such a way that if user moves this speed, what will be my switching speed? So that input you can give it to the RF engineer, and then that will be an input for RF engineer to design particular antenna array. So it is an opportunity for every engineer. So whoever you are, and also electrical person engineer also can take up this work, because in electrical point of view, what happens is, see, you have to the power supply is very, very critical, and how much power, how planning you have to do. So that way, electrical engineer also play a major role, and also mechanical engineer also. Why? Because mechanical capability of the, you can design any antenna, but finally mechanical person has to be manufactured, right? So they have to give this kind of scenario we can use, and this kind of strength material they can use for support and everything. So they can only give you the idea. So if you are a mechanical engineer, then you can propose for a different kind of opportunities as well. Next is the CAD modeling analysis. Okay, as I said, we are going for active integration. The CAD modeling become much complex, because you are going to handle with not only simple antenna, you are going to handle with the active circuits and everything. So that time what happens is, it will be computation complexity will be much higher, because it's a very much complex design, multi-layer, and large number of vias, thin substrates. So these are all the much complex, because you have to choose accordingly, and computation complexity and time. Next is the antenna perspective. Okay, what are all the challenges are there? First is that antenna element design. So you have to support. I think in one of the conference I came to know, one of the stringent condition is that you will be provided 20 centimeter by 20 centimeter, not so, sorry, 25 centimeter by 15 centimeter space. In that, you have to design massive MIMO antenna with two bands, dual band, dual polarized. So in that case, you have to select antenna element design will become very critical. Next is that feeding methods. Okay, what kind of feeding you are going to use? You cannot use just a corporate feed network or a series feed network. Okay, you have to go for multi-layer feeding as well. So otherwise, you cannot feed all the elements. It will become much complex. Next is the impedance matching. So when we go for multi-layer, the impedance matching of each element will become critical. Okay, in element design itself, we will feel that impedance matching will become critical, because the conditions are dual polarized, multi-band, large bandwidth. So multiple things are there. So if you are achieving impedance matching will become very critical, crucial. Next is the element spacing. So when you are achieving impedance matching, then you will place in the array environment. There you have to optimize the element spacing as well. You cannot just put a 0.5 lambda. That is the default thing. You can't just put. You have to optimize the spacing as well. Why? Because radiation pattern will be affected. Antenna. Selection of active elements also will be a crucial. You can select diode or capacitor or anything. So for switching, for activating particular elements. So in that case, so selection of active elements will become crucial. So if you are a good in device engineer, okay, if you are good in electron devices, you can help in this these kind of, you can design different kind of devices, and then you can propose this kind of devices can be used for this particular application. This kind of devices can be used for this particular switching. This kind of scenario like that you can propose. So that kind of opportunity is there for the if you are good in electron devices or electrical engineer. Okay, and beam forming. So algorithm is very important, because I cannot switch the beam as like I want, because when it is purely based on when our base station is there, user is moving in a speed of, for example, they are providing that they are supporting the speed of 300, more than 300 kilometer speed. So how much speed how much how complex will be the algorithm, because it has to track the user on the go. So the complexity of algorithm will be very much higher. And you can if you are good in algorithm, be a signal processing engineer, and you are good in mathematics as well, then you can propose different kind of algorithms. It is you can take up the project on this. It will be a very useful for you in getting job as well. So beamforming network, and which means so once you design the algorithm, the next I have to implement that in the antenna array. So for that, I have to antenna array elements are designed. Now I have to switch the beam as proposed in the algorithm. So that case, I have to design the beam forming network as well. And crosstalk. That's what I was telling. When the element spacing are not proper, and when feed lines are not properly designed and not properly routed, then crosstalk will come into picture. Antenna mutual coupling, both are almost similar scenario. Okay, and impedance matching mismatch. So because impedance mismatch will come whenever you want to implement this algorithm with the beamforming network is also ready. Everything is ready, but when you are integrating with the other circuits and everything, that time impedance mismatch will be there. So you have to work hard on that. So impedance mismatch means you have to have a matching circuit network. If you are good in matching transmission lines, you can propose a different kind of impedance matching network for this particular scenario. Okay, and phase control resolution. So I want to switching in, for example, I have designed the algorithm to switch the speed, for example, 2.5 degree. Okay, switch the beam 2.5 degree. Whether actually we are getting 2.5 degree switching or not, that we have to ensure. That resolution we have to see. Second resolution, phase resolution, is that, for example, if I excite this element but with some amplitude and phase, okay, and this particular element with some amplitude and phase, okay. So this phase is whether that feed line offers that particular phase or not. We will have surely we'll have a tolerance, right? So we cannot have, if I am designing for a phase 225 degree, my feed line will not give 225 degree. It will be a plus or minus something. So that's why the phase control resolution also will be a crucial problem over here. Okay, and so okay, you're done with the everything. Okay, now when you go for fabrication, you will feel you will get a lot of surprises, because in my project also I have done for ISRO own project. I have done with one substrate, but availability of the substrate was different. Then I have to come back and then design accordingly. So main problem will come is PCB substrate selections. So when it comes to millimeter wave, it is very much restricted. So, and you will not get as substrate. Please, before design, you please consider what all substrates are available in the local market and available at least in your country or in our country. Because otherwise what happens is, at the end of the day, you have done all the struggles, you have done very good, fantastic job, and you have done phased array and everything. Finally, you will see that substrate will not be available. So then your simulation will become waste. Then you have to go for other, because optimization of matching and input and everything, integration, everything will plan according to the PCB substrate, because dielectric constant play a major role. So that's why you have to please explore and before you design. Printer antenna,
Sir,
RF circuits, and substrate losses. What? Madam?
sir, sorry for the interruption.
Yes, madam.
Participants are eagerly
Okay.
waiting for your answers. Lot of queries are there in the
Oh,
chat box,
sorry.
sir. Please look after the
Okay,
questions.
okay.
Please. Yes.
Okay, so okay, we'll like a kind of break we can take, and then we can answer these questions. Oh, sorry, it's already 3:40. Okay. Go to subscribers. Jairam M, what about the effect of 5G on human health? Okay, so that is the big topic is going on. I think you might have seen some rumors are coming that whenever they enable the 5G, then several birds are getting. But that effect is there, but still they are not witnessed. Okay, 5G and several regulatory, for example, TELAC that I will be discussing. So they are giving stringent conditions on base station emission. Okay, but and the network, when they implement the network, and then only they'll come to know how human health. Even in 2G also it was there. Now they try each country is play crucial role that they are controlling the base station emission power and everything. Is 5G is secured? Of course it is secured, because several security algorithms are there, but it is a kind of trust you have to have. That's what I believe, because 5G is secured means you might be thinking that several devices are connected, so our data might be stolen or by somebody. So even now it is is there, right? So in Facebook or WhatsApp, you are sharing many things. So that is the Gmail, Google, and everyone is storing your data. So if you are believing this, then we have to believe that also. Okay. Next is the important difference between 4G and 5G is that the main difference is that we are having different kind of architecture where you can add a new feature, or you can implement any new feature you want, and very large data rates, and our low latency communication, especially there in the 5G. Okay, that is the major difference. And architecture wise, they have a more flexible than the 4G. Architecture wise, network architecture wise is much more flexible than the 4G. And next question is, do you expect that will be 6G in the future? Yeah, of course. Now 6G, the discussions are on since last year. I think, I believe last week also I saw that one special conference are going on 6G. I think they are. I believe that, I'm not sure, but they are talking in terms of terahertz communication. Now we are talking of millimeter wave communication. In 6G, they are planning for terahertz communication, because a lot of free unlicensed bands are available in the terahertz. Not many interferences are there. That's why they are planning for terahertz communication. But it will not be paradigm shift, like from 4G to 5G was a paradigm shift. But in 5G to between 5G to 6G, I don't think it will be a paradigm shift. Okay, how 5G is better than 4G? I think I have answered some of the questions. So one is that high speed data rates and low latency, very low latency, and you have a number of flexibility in the design. And also, in 4G, you cannot integrate every technology. For example, LoRa, Wi-Fi, and everything. You cannot integrate all those technology with the 4G technology. But in 5G, that is possible. Okay, you can, you can bring, if you have a very good network, like a Wi-Fi or LoRa and several communications are there. So here, what they are in 5G, what they are using, that they are making use of those technology for providing. For example, if you are going to indoor coverage, right? They are spending a lot of money on indoor coverage, because indoor coverage is bringing indoor coverage is very much expensive than the terrain coverage. Because in 5G, what they are doing is that when you are calling, your call is there, you are calling in 5G network outside. Okay, when you get into the building, what happens is that this call will be routed through Wi-Fi network. I think some Wi-Fi or some Wi-Fi 4 technology also recently came. So voice over Wi-Fi also technology is there. So that is towards 5G only. What is the advantage of 5G challenges and opportunity in our daily life, and what affect the environment health, sir? So that thing I already, because a lot of connected devices will be there. Of course, it will be a harm, but it is our responsibility to take care of these things. And daily life, we will become, everything will be in your hand. You need not to go and switch on your TV, and that is not good. But even then, the 5G, these things will provide, and you will have a flexibility of. And one good thing is that the education transformation. So many technological transformation will happen in this 5G. And what is G stands for? G stands for, which is generation. 2G means second generation, 3G means third generation, 4G means fourth generation. That's all. LT means, you see, long-term evolution. Because from 3G to 4G, there was some bit paradigm shift was or a very good amount of shift was there. That's why they differently called as a long-term evolution, like kind of thing. And how much speed in 5G network? Until now, I think it's in hundreds of Gbps, but in future it will be terabytes. Okay, and it's running short of time. After question, okay, sorry. Okay. More number of towers and antenna required compared to 4G. Why? Because see, we are going for a millimeter wave. So with the millimeter wave, you cannot, millimeter wave will not pass through for a long distance. So hence you are going for small coverage. So cell coverage will be, small tower will be there. In every building you may have to implement. That's why we go for these things. Okay, I will rush up because we have discussed enough. Okay, I just run through the slides and then. So these are all the general challenges are so getting compliance is very difficult, and regulatory compliance. For example, for India it is there, Department of Telecom and TDSI. So for you, please go through this white paper. It is very much informative. TELEC is responsible for Japan regulatory, and KCC is for Korean regulatory. Emulation is also a major challenge, because you have to emulate. Emulation means, see, you will create a network scenario. If 5G has this many devices, it's connected this with this speed, it is moving. What will happen to device? So like how node B has to react, and how everything. So that you have to emulate through emulators. That we call it as the emulation. Okay, from the practical to coding, like simulation is called as emulation. So we have a device testing and node B testing. I'm involved in device and node B testing as well for 5G and SCUTX devices. So now simulation point of view, you cannot have individual simulation. You have to go for co-simulation. For example, if you want to design an antenna, so you have to go for CST Studio, for example, ANSYS or anything you want, you can add. So you will go for a co-simulation with the advanced design system, ADS, because ADS will be used for designing the amplifier and everything. And CST Studio will be used for antenna design. So here, output of this one will be fed into here, and likewise you have to optimize this whole design. Okay, and this is how it will look like. For example, input circuit and output. So matching network will be integral part of the simulation, and then amplifier and everything, antenna, everything is integral part of the simulation. So therefore you can reduce this workaround time. And this is the phased array. You can see that. You can see that. See, by varying the phase and amplitude of the each element, you can control the sweep, the beams. You can see that this is there in the Balanis book. You can see that. So how each elements are there spaced upon with that particular spacing. So by controlling the amplitude and phase of the each element, you can steer the beam wherever you want, like this. So you can steer the beams wherever you want. Okay. And antenna measurement, especially it is very antenna measurement or general device measurement. It is very crucial, and we normally test at far field region. So this is what is the 2D square lambda is what we use for far field distance, and then this is how far field distance only we will get a planar kind of waves, and so these are all the measurements. So when you measure, so have a transmitting antenna, and this is the DUT. If you sweep, rotate this antenna, you will get this kind of patterns. The next type of measurement thing is that that was general measurement setup. It's next one is the anechoic chamber. So this is how any antenna device or vehicle or everything will be tested. Okay. Next, these are all the you can see that big satellites are being tested. And another approach is that 5G OTA testing. So if you are good in OTA testing, you can get a job in a 5G industry, because OTA means over the air testing. You are mimicking the real time scenario in the lab itself. So in this case, if a beam is switching, how we can measure by rotating this mobile azimuthal direction and also the vertical elevation direction, so that you can find out which beam, which direction the beam is directed. And also, and other method is that this is for one antenna will be there as a receiver, and your transmitter, and your mobile will be rotated in this fashion. Or else what I can do is you can keep the mobile, and then you can place multiple number of antennas. You can for example, if your beam is in this direction, then what happens is this antenna will get received the signal, so that you can find out which direction the beam is on. Okay. And these are all the design tools, different design tools for simulation, and for testing. You can use the Keysight equipments and Android or Andas or YV solutions. So to summarize, so we have been discussing about, I think I have taken half an hour, 20 minutes more. I'm sorry. So features and use cases of 5G, and overall number of challenges involved in the various levels, and various opportunities also we have been discussed. So, and simulation, different kind of simulation we have discussed, and simulation tools and measurements, and so that's all. So thank you for your time, and thanks ThickNess Learning community for providing me this opportunity. So if you have any further question, you can ask. If time permits, I'm able to answer.
The last 2 questions are waiting for you.
Is for 5G communication more number of towers antennas required? Yes, it is required. If you are going for millimeter wave, it is required. If you are going for sub-6 gigahertz, it is same as 4G. Okay. If your band is, if you, for example, in India, some operator want to implement 5G, if they are going for sub-6 gigahertz, then same LTE tower itself they can use. Same number of LTE tower can be used. Okay. But if you are going for millimeter wave, you have to have multiple number of things, because attenuation will be much higher in the millimeter waves. The second is that how 5G could be used in education, online training, business. Main challenge is to introduce opportunity for the industry. So one is that now most of the, you might be knowing that most of the education are going on virtually only, so not in practice. So in future it will be it will become usual habit. That is one thing is that. And also you can see in virtual education, with the current internet speed, you cannot do many things. For example, some kind of virtual education. For example, you want to simulate or you want to, one particular advantage I can tell you that now MATLAB has gone to cloud. Okay. So in 5G, when you have 5G, now it is very difficult to get, if you're running very big program, then you will not get the results immediately because of the speed. But in future, if you have very good amount of speed, you will get instantly, like your real laptop, real MATLAB, if your software is installed in your laptop, how much speed, whatever speed you get, right? Similarly, you will get in for even the MATLAB cloud. Similarly, they know various design tool manufacturer, EM tool, simulation tool manufacturer, designer, what they have gone for, they are all gone for cloud solution. So when 5G come into picture, that time you will have plenty of data rates. So that what happened is you can design whatever antenna, how much whatever complex it is, you can design, you can making use of the cloud technology as well. Okay. And
Yeah, sir, excellent.
okay. Okay, thank you. If you,
Sir, can you stop sharing, sir, please?
yeah, please. Yes.
Yeah, ladies and gentlemen, yeah, very warm and pleasant good afternoon to all. Never stop believing in hope because miracles happen every day. With this excellent quote, it gives me an immense pleasure to propose the vote of thanks for this wonderful occasion and webinar on 5G challenges and opportunities. I would like to thank today's resource person, Dr. V. Lingasamy, Technical Lead, HCL Technologies, RF Engineer, Keysight Technologies, Bangalore, India, who honored this program despite his busy schedule. Sir found time to grace us with his wonderful lecture. Sir, really, it's a very useful, wonderful session. Thanks a lot, sir.
Thank you, man. Thank you.
I also express my sincere gratitude to ThickNess Learning Community, Young and Dynamic Director, Mr. Kritik Raja, for his backing and arrangement to make this webinar grand success. I am also very grateful to ThickNess Learning Community Advisors, or Dr. R. Dhanashekaran, Dr. M. Nirmala, Mr. Bhaskar, and Pranesh for their encouragement, valuable contribution, and wonderful support, because we have received more than 350 plus registrations from various states of India and different parts of the world. So we are using two different platforms like Zoom and YouTube live streaming. I express my special thanks to ThickNess Learning Community patrons, Unimax Technologies, Coimbatore, and Aurora Nuts, Chennai, who supported behind the success. But not least, I would like to thank all ThickNess Learning Community beloved participants from national and international for showing your interest in this webinar, for making this event as a resounding success. Without you, we can't do anything. ThickNess Learning Community upcoming webinars are Let Us Learn Cloud, Life, Chance or Choice, Insight of UPSC Examination, Integration of Image Processing and Artificial Intelligence for Intelligent System Development, etc. Once again, I thank one and all present here. Thank you very much.